All right. So as for today, we're going to begin my two favorite chapters. All right, higher order differential equations, but first Laplace transforms. Laplace transforms are really, really great. And be aware, we're only going to focus on this in this class, but there are Fourier transforms and lots of different Taylor transforms. There are lots of different types of transforms, all right? But Laplace transforms just kind of like epitomize differential equations. So we're going to start with the definition, and we're not going to use this for long, just so you're aware, because transforms are all about using a table of transforms to adjust them. But we need a few definitions before we get on the way. The biggest one is piecewise continuous, and you may have already seen this. It really means that on an interval, you can have an infinite number of subintervals, and this is still considered piecewise continuous. Is this continuous? Just in general, continuous. Our definition of continuity from Calc 1.
Oh, man. That was a long time ago. I don't think so.
No. Because, right, when you draw it, I have to lift my pen, right? So, but, all right, and I have problems with the derivative right here, okay? This is clearly a discontinuity here, but notice, all right, everything is continuous as far as piecewise continuity goes. The whole idea is that does this head towards positive or negative infinity? No. So on that entire interval, this is what we call piecewise continuous. Definitely not continuous via our definition, because if you recall the definition, the left limit and the right limit have to go to the same value, and the derivative, all right, have to exist. So I mean, I have issues here. I was like, I have issues here, I have issues here, as far as the official definition of continuity goes. But, all right, it is continuous on this, it is piecewise continuous on this interval. So the official definition of Laplace transform, and the notation goes back and forth. So the official notation, a lot of times when you see it typed, kind of looks like this, but we write it like this because that's easier to write than making a perfect L like this. So we tend to just do like capital cursive L. The definition, all right, is from 0 to infinity of e to the negative st f of t, where f of t is the function that we are transforming, all right, dt. So before we actually get into that, we need to back up. Oh, and then as a note, so we write the notation as the capital L a lot of times, but more often than not, right, we convert that all the way to capital F of s. So we convert our t's to f's. And that's the whole idea of the transform. This is the Laplace transform, all right? That we created this new function with a new variable from one variable to another, and that's all the transform is. And the idea is that we're able to solve that simpler than solving the initial function. Because it's just a transformation. That's the whole idea. Okay, before we get to solving the official definition of Laplace transform, we need to back up and we need to remember just how to do an improper integral.
But you have to set infinity equal like a, take the limit of that.
Ah, well done. That's exactly what we do. All right, and so for this one, all right, this is not the definition, but it's similar if you notice. And we are identifying c as not equal to 0. But you are absolutely correct. All right, we are going to turn this integral into the limit as a approaches infinity. 0 to a, e to the c t, t. And then simply just evaluate it. Okay, so once we end up with this, all right, we have two cases. Because, all right, case one, we identified C not equal to 0, which means what are the two options that C can be?
Your negative.
Yeah. Just for C. So C can be below 0 or above 0, right? Since C is not equal to 0. So case one, all right, we're going to do C is less than 0. And this means that the limit, as A goes to infinity, of our thing would become -1/C, right? Because this guy blows up, right? This goes to infinity.
C is negative, shouldn't it be positive?
What? Oh, no, I'm saying that when C is negative, I was like, I'm just putting it in.
Oh.
C is negative because this blows up to infinity, 1/infinity, this whole thing becomes 0. I mean, yes, I was like, I skipped all the steps. Because when we put it in, this that we have from above becomes. Yeah, except it's just below 0. That's actually the irrelevant part. Because what I want to say. Because it's still just gonna, that thing, C is below 0. That just moves to the denominator. That becomes infinity, 1/infinity is 0. So you just end up with the second piece. The first piece then, right, case 2. C is above 0, and exactly the other problem, that limit blows up to infinity. Which means that's not helpful. So the whole idea, all right, is that the limit, or the and so the whole thing is that the integral, all right, results in -1/C as long as C is below 0. Right? Because yes, the value would be negative, but I could put it in there. All right, so negative, negative. But it has a solution as long as there is a restriction. And the biggest thing is that we're going to see that for Laplace transforms, we're going to have restrictions on our function often. And that's what we want to emphasize. So now let's start with the simplest case of a Laplace transform. All right, Laplace of the number 1. So back to our definition. All right, and notice the definition was pretty close, but now I'm defining, right, Laplace is this function. If I just put a 1 in here, that looks pretty close to the integral we just evaluated. So Laplace transform of 1. So now e to the negative st of 1 dt. And this is actually almost exactly what we just evaluated, all right? Because we evaluated e to the ct, 0 to infinity. Now we have e to the negative st. So the only thing we're changing is we're replacing c with negative s, which means I can actually evaluate that because I already know the situation. This becomes -1/-s, all right? Since I'm just replacing C equals negative S. And with my restriction, C had to be below 0, which now becomes negative S has to be below 0. So the Laplace transform of 1 is equal to negative 1 over S, where S is greater than 0, right? Just moving the signs. And this, all right, is basically how we could solve a lot of Laplace transforms using the definition. And the big thing, notice, all right, we have a restriction on S. That is all transforms. The minimum restriction is this. The minimum restriction is S greater than 0. That's where all of them start. And then basically we will some have further restrictions. Oh, my S greater than 5 or whatever. So, all right, unless something in the problem identifies it, if it's not specified, S is greater than 0. It can be, pretty sure we have some, maybe S is greater than negative values. So it depends on the problem. But, all right, if you can't identify a restriction, it's S greater than 0. To that end, I could do another one. So using the definition, I want to do Laplace of AT. So now my function f of t is AT. And then we can mess with this just a little bit to get this into e to the a minus s of t dt. And once again, I have it into the same form that we have above, but now c is a minus s, which means this is negative 1 over c, where c equals a minus s, which becomes negative 1 over a minus s, or that would be s1 over s minus a. And the restriction, we had c is below 0, which now becomes a minus s is below 0, which becomes s greater than a. So we can evaluate just by doing those substitutions. Now, here's a big thing. There's a couple of home fun problems, nothing excessive with actually doing these by the definition. Most of the time, we're going to use the table as we can see. But I want to at least talk about this, and again, this is in the notes. I was like, I could then do it for sine. I do a similar thing, but with sine, I had to go a little bit more in depth because I do integration by parts. I do integration by parts again. Oh, but notice right here, e and sine. What kind of integration is this going to be?
Cancel. I forgot the term for it.
Cyclical or circular, however we call it cyclical, circular. All right, it's going to be two things that don't go away, right? So you have to resolve them. All right. And I would end up with the two limits. All right, so I had it. And then you would solve it down and find out that the Laplace transform would actually be a all over s squared plus a squared, provided, once again, s is greater than 0. Now notice right here, all right, you can look at this one. When we look at the one above, it makes complete sense that s is greater than a, all right, to keep that from being negative. When I look at the sign on here, is there anything in the denominator or anything that looks like it restricts it? No, which means back to the standard restriction of s greater than 0. So Laplace transforms are going to be messy, and be aware occasionally you will see the full definition of a Laplace transform, which is negative infinity to positive infinity, right? The full type 2 improper integral, right, that we discussed, and you would break those into pieces and do each one, right? The whole thing is that most of the time with Laplace transforms, though, we essentially have a heavy side function in there or piecewise function, all right? An on-off switch where the function starts at 0. So even though you may see this notation almost every time, and we're going to get into more of this at the end of chapter 5, that the function, all right, is restricted to particular domains, which means the 0 to infinity is equivalent to the negative infinity to infinity as far as Laplace transforms go. All right, so we just don't solve them by definition that often. I want to make sure you see the definition, but the whole idea of anything with transforms, Fourier transforms, or Laplace transforms, you have a table, okay? And this might be the one thing I didn't print for you guys, so make sure you print this. All right, it's on campus. The table is how we do Laplace transforms all the time, because we're going to have to go both directions, and there's going to be ones that we see over and over again, and you just don't want to constantly go back to identifying that transform over and over. Notice the two that we proved, 1 over s and 1 over s minus a. Okay, and then I had the proof there for sine as well. With all these, basically, this table is a near exhaustive list, and the reason is that between a couple of these other ones that simplify, I can find basically everything as combinations, right, or variations on those main functions that we have. Without a doubt, like 1 through 10, and then 35, 36, and 37 are like massively important. Couple of notes, all right? It is not exhaustive, but it's pretty darn close. It's everything that we're going to look at. Just to recall, hyperbolic functions, remember the actual definition, right? It's the sum, difference, catenaries of exponentials. And so the hyperbolics are very, very similar. So watch out when we go inverse Laplace transforms to Laplace transforms. Watch out that it's literally just a sign difference in the functions, right? So cosh and cosine, notice the exact same equations. This is the only difference. And then just some other notes. The gamma function, heavily used in statistics, by the way, all right? It is basically a factorial function. And so a couple of special cases of this factorial function just because they're up there. All right, so very good table. We're going to go back and forth and we're going to practice using this. Before we get into the details of the table, some really, really nice things about Laplace transforms, and almost all transforms abide by this, because the linearity property, if you don't have this, then no matter if you're multiplying by a constant and some another constant, you have to redefine a new transform, which would just be asinine, right? So the whole idea is that constants always can come out, and you can look at each piece, right, of an additive function individually, and you don't have to worry about identifying new Laplace transforms. So we identify the base function, and then we put it into our transforms. And then, yes, once again, I can't emphasize normal trig functions and hyperbolic. The difference is literally a sign. Okay, so let's practice with our Laplace transforms. And so all we do is we have this and we go to the table. All right. So I have an E function, all right, a T function, and a number. But given our linearity property, so when I do the Laplace transform of this whole thing, Now, I'm writing this out all the way this time, but most of the time, after you write, like, I'm doing a Laplace transform, I pull it out, and then we just identify what you're transforming, right? So I have an E function, T cubed, and 1, all right? So that's the big thing. The 9, -9 comes out, and it's Laplace of 1. We already know that one. That is number 1 in the table. All right, so let's see what we're looking at, and then we'll identify that. So we're starting up here. So the 1 is the transform becomes 1 over s. All right. This is the function f of t. All right. And we're starting going to the transform. So we're going right at the moment. We will go left when you start in the function s. And this is inverse Laplace transform. So we go left. All right. Then I have a function e to the at. And basically each time you just identify what a is. Right. So we had a 3 and the other one was like -7 or something. All right, so we got those two, which are 1 over s minus a's. The only other one we hadn't looked at yet, all right, that we didn't prove initially, all right, is this guy. So I have t cubed, right? So all you have to do is identify n. N is 3, all right? So that means 3 factorial divided by s to the 3 plus 1. And that's literally all transforming is. Okay, so this becomes 1 over s minus -5, right? So this is number 2. We'll just identify number 2, 3, and this is number 1. Plus 1 all over s minus 3 plus 5 times. What do we say? 3 factorial all over s to the 3 plus 1 minus 9. Times 1 over s. Now the big thing, the hardest thing maybe about Laplace transforms is what variable are we using?
The a or
What variable are we in now?
the s?
What's the problem with s?
5.
Okay, so make sure you are uber clear. All right, that's a 5, right? That's a 5. All right. The biggest problem, without a doubt, is since it transforms to s, and we started in t's, s's. God, I forgot pluses, 5s. Like, I mean, so make sure that you're careful with your handwriting. And then I could simplify this down: 6 all over s plus 5 plus 1 all over s minus 3 plus, okay, 5, 6, 30. 30 all over s to the 4th minus 9 all over s. As a note, so sometimes I see people, you convert these to dollar signs too, whatever is helpful to you. I was like, so as long as you identify it is a different variable. And that's basically that. All right, let's do some more. All right, so cosines and sines, and cosines and sines are pretty close as well. So with sine, it's a all over s squared plus a, and this one's just s all over s squared plus a squared. So identifying the a, which is the value inside. So Sign is number 7. Times the A. That's and then simplify it down. All right. And so we have 4s squared plus 16. All right. So the S, I was like the S squared. Now be aware, putting it under one denominator is actually not optimal. All right. When we start pulling them apart, we'll see how much trouble we get in when we do that. All right. Some hyperbolics. So sine is number 7 with A equals 2. And the hyperbolic sine all right, number 17. And so notice, right, number 717, it's literally just plus and minus. So that was number 17 with A equals 2. And then simplifying down, 6 all over S squared minus 4 plus 6 all over S squared plus 4. Oh, yeah, I was getting too ahead of myself. And then, all right, we want to make sure, all right, we are identifying our restrictions. So I could definitely say S greater than 0. All right, looking at the denominator here, is there an additional restriction?
S can't be 2.
So if it can't be 2, that means
Has to be greater
than 2. You're exactly correct. All right. Yeah, let's back it up. Let's get too ahead of myself. How about this guy?
S greater than 0.
That's greater than 0. Exactly correct. All right. And then back to this guy.
S greater than 3.
That's correct. And so you're absolutely correct, right? You're just looking at them all, right? That one's 0, 0. Oh, that one's negative, which means, all right, the minimum, all right, is s greater than 3. It's whatever it cannot be, and then we put that restriction on. All right, plus transform of e to t cosine. Okay, so this guy's clearly number 2 with a 3. This is number 8 with a equals 6. And that one looks new. All right, E3t cosine. So, all right, there are some options to combine multiplicative functions. However, E cosine, E sine, and their hyperbolics are so common that we actually have the functions for them. So we're going to see that we have some options to create other functions, but these ones tend to be so commonly occurring that we literally just have these. All right, so that one was E cosine, so number 20, all right, A is ER. So number 20 with A equals 3 and B equals 6. So 1 over s minus 3. All right. And then, all right, so that simplifies down. What's our restriction?
Greater than 3.
Yep, greater than 3. All right. This one. That actually doesn't matter. It's only that one. All right. Let's do some more of those transforms. All right, so T hyperbolic cosine. Okay, hold on. I see T cosine. That's close. Do we see hyperbolic? No. So T multiplied by a function. Notice that I've got this version with T times E. It's a very common thing, right? Multiplying a T by either a cosine or a hyperbolic. This guy right here, all right, number 30. Any power of T multiplied by a function. This says that you identify the transform of this function, and then what's this notation here in the superscript?
En, like to the power of?
Oh, almost, not to the power of, to the derivative of. So this actually says take the derivative of the transform of that function, that power of T times. It's actually pretty elegant if you think about it. Because I was like, yes, you have to do a bunch of derivatives with like a 20th power. But a transform that you don't have to readjust for every multiplier, that's actually pretty elegant. Just so you're aware. Okay, so we're going to use 30, and I think, was this? Oh, it was just the first power of t. All right, so we need to use number 30 with n equals 1, because it's just the first power of t. Now, the good news is, all right, is that a lot of times, so t to the first power, f of t, just see what this becomes. That transforms to -1 to the first power, the first derivative of s, which means that we just need to do negative the first derivative of the transform of the function. In this case, f of t, what was our function? What was the main part of the function?
Cosh.
Yeah, it's just the hyperbolic cosine cosh. And then our transform becomes, which is, right, number 18 with a equals 3. And then now we actually need the derivative, because what we're actually looking for is the derivative of this guy, and then we'll take the negative of it. And then how do I take a derivative?
Quotient rule.
Yeah, quotient rule. Yeah. So, D low. Square the bottom and away we go. Finally, our function g of s, let's call it, which we're actually looking for, which is negative the derivative f prime of s. To squared minus 9 minus 2s squared. So negative, yeah, which becomes negative s squared plus 9 over s squared minus 9 squared. So multiplying that out, and it actually negative, I already have a negative in here actually, so negative of that just becomes the positive. And then can't forget, what last thing do we need?
Oh, S restriction. It's got to be greater than 3.
That's absolutely correct. And so that is actually a very, very common approach. Now, good news for us, we're never going to see super high powers, but we might have to do it more than once. For example, now when I look at B, what do you see?
Squared, so.
It's the same thing. Now, always first, look at the table, see if you can find a table. Do I have a t squared sign in here? This is a pretty extensive table, just not completely exhaustive, right? So it would take forever. But using this guy number 30, it's a very, very common thing. But now we're going to use number 30 with n equals 2.
So let's call it h of t. That becomes the transform h of s, which will become -1 to the second power, second derivative of the transform. And -1 to the second power just means it is second derivative of the transform. Since we have our function f of t, which is sine of 2t, that becomes our transform, f of s. And that's the days. This is number 7. It's 2. There's on top right there. 2. And then we get 2 derivatives of this guy, which again would just be quotient rule. And since what we were looking for was just the second derivative, actually that is our solution. And then what is our restriction?
0.
0. Those are the easiest ones, right? Because it's just 0 every time. So linearity property every time, 10 to the 3/2 power, right? That just comes out. Constants, get it out of the way. And I really just wanted to do that so we could emphasize. Is this one on here?
Is it decking 3?
Nope, it's not 3.
Oh, it's a fraction.
It's on here. It's in the top half of it.
6?
It's 6. All right. Once you get fractional exponents, so important to note, right? 1, 2, these are natural numbers. These are natural numbers as a restriction, but a natural number minus a fraction becomes fraction. So half powers, okay? Now notice square root, because that one's super common, is its own, but square root is just a special case of this guy. So this is actually 6. 5 is just a special case of 6. This, all right, is basically, notice what we have here. It's an odd factorial. That's what this actually represents, right? And 2n minus 1, that's how you calculate an odd number. No matter what you put in there, that always ends up odd. Just FYI. And so basically this, all right, notice that 5 and 6 are similar to 3, all right, but they represent fractional powers. So if my power is t to the 3/2, what is n to make this work?
Would it be the 3/2?
No, 3/2, because remember, it has to be a number 1, 2, 3, 4, 5.
Oh,
So what number is n to become t equals 3/2? T to the 3/2.
no.
Put in a number like 5. 5 minus 1/2 is
3/2? No.
4.5. 9/2.
9.
Okay, so now we know that. So now what number?
What is 3/2? That is, I'm overthinking it.
3/2 is 1.5. 2, yeah. I was gonna say, I was like, you're like, wait, oh, I don't know what I'm doing. Yeah, no, it's just 2. So you put 2 in there, but it's always important, right? Every time, that's why I'm saying, I'm using number 10 with A equals this. These are even more difficult because 3, 5, and 6, well, 4, 2. I was like, these ones, you have to put it into the function because the transfer over, this is one where, I mean, I'm looking at the table straight out too. So yes, this is number 6 with n equals 2. And then we can actually transfer this over, all right, using our equation. So that's still 10 free hours power to 1. And actually go look at that equation one more time. So if n is 2, right? This is a factorial up to what? 1, 2. So it's just 1 times 3, right? 2 to the 2 to s to the 2 plus 1/2. So just be aware. That's why it's so important, because when you transfer it over to the transform, I was like, you got to make sure you're putting everything in. So this is 1 times 3. This guy then root 3. Then this is 2 to the 2. This was
There's supposed to be a 2n minus 1 on the top.
all the way up to. It's a factorial, so I already got it. 2 times 2 is 4, minus 1 is 3.
That's how you got that?
Yes.
Oh.
It's a factor. It's 2n minus 1 factorial. Really? That's all that represents.
Okay.
So if n equals 2, then it's 2 times 1 minus 1 is 1. 1. So I got the 1, and then the 3.
Okay.
So that's that whole thing is just factorial. 2n minus 1 factorial.
So the part where it says 135 is just
Oh, it was just, yeah, starting the factorial. Because I was just representing it's odd factorial.
okay.
Right? Yeah, it's just a fun. I was like, since you haven't had a math proof class where you prove how numbers are odd. Okay, and then this guy is 2 plus 1/2. And then it just simplifies down, yeah, to the 3. It's fine. Just look that out for like 2, 4, s to the 5/2. Yeah, and the simplification, all right, not nearly as important. It's just identifying and then yes, using that formula. That's kind of why I picked that one, because that formula is messy to use. All right, and then what's our restriction? 0. Technically, there actually is s cannot be 0 on this one, so that one more clearly identifies than standard. It is 0. Okay, T. Okay, t to the g prime of t. That kind of looks like 30, 100%. Right? Because I have a t and I have a function. Oh, that's pretty close to 30. But I was like, I want to also identify, all right, that 35, 36, and 37, all right, are heavily related when you take the derivative of the function being transformed. All right, so we're going to use some combo of 30, right? Because I have t times g, but then I end up, all right, with having to take a derivative, and these ones, all right, 35, 36, and 37, all right, become very, very important, all right, very soon, as we're going to see. Okay. All right, so definitely number 30 with t equals 1. And so we see how often we use that.
Okay, I'm gonna call this guy K. All right, because using number 35. Just the derivative of the Laplace transform. So K prime, okay, since we need the derivative using number 30, all right, in order to do the derivative, I've identified that the G of t using number 35 is that definition from the table. Right, so it's S f of s minus f of 0, but since we have g's in there. When you have a derivative of the initial function, and this is why Laplace transforms are so nice, that I can do a derivative with the initial function that actually transforms into something in a Laplace transform. And that, right, it's designed for derivatives. That's why we use so many derivatives to adjust this. All right, so this is literally just the product rule. And so the idea is that all I'm identifying is that when you put these back in, when you do the derivatives of these, you end up with this repeated sequence, and that's the emphasis of number 35, 36, and 37. So that is basically this process we extend out when we start doing higher order Laplace transforms, and you can just repeat this over and over and over again. And these end up being very, very useful transforms, all right, with their functions, and when we start doing with heavy side functions as well. And so that's all the point of this what is that Laplace transforms are designed to as multipliers and to be used as derivatives of the functions. And so that's what makes them just so versatile. Fourier transforms, they're designed, I mean, mostly it was designed for series, right? But Laplace transforms were designed for derivatives, and since they were designed for derivatives, they can be solved with algebra. And that's what makes them just so nice. They can be solved with algebra and some low-level calculus. That's why Laplace transforms are so fantastic. All right, we're gonna pick it up right there next class.